So let me start by thanking Ookami team to give us the opportunity to get access to the Ookami machine and also to present in this meeting. So I want to talk about in our research project, which we are working on. We call it active link consolidation. So first of all, let's have a glance at SVE. We know that SVE is a vector-length agnostic extension for ARM processors. It supports a variety of vector lengths from 128 bits to 2048. We know that it has a powerful vector predication support. So previous vector extensions, such as Neon for ARM and AVX for x86, they had simpler predication support. But here in SVE, we have per vector predication, which means that for every vector of data, we could have a corresponding vector of predicates. And the third good thing about SVE is that it proposes special vector manipulation instructions that are used to move data between the vectors, and they are really fast. So knowing these three things about SVE, we are trying to solve a problem, a challenge in loop vectorization. Let's start with a simple example. So let's say we have a loop where we have a conditional inside that, which is an if statement. It has a single statement in the then block, and we have also an else block, which has another simple statement. So the way to vectorize this is through if conversion, a compiler transformation that linearizes the code. So the result code would look like something like this. So first of all, we make a vector of predicates, a mask vector. Here in this case, it's very simple, just four elements of the count array. And then for the code inside the then block, we are storing in the AI the result of the multiplication of these two indices of the array B, these two vectors of indices of array B, and we are only doing this when the mask vector is true. And so for the else block, it would be quite similar. We are doing the addition of those loaded vectors, but this time we are doing the store operation only if the mask is false. So for the false lengths or inactive lengths of mask vector, we are doing the operation. So you can probably notice the problem that comes here. We are passing the mask and the not of mask, which are mutually exclusive conditions. So during execution time, only one of these two instructions will be committed, and the result for the other one is wasted. So that is, we are doing the computation, but we are just discarding the result. So to see how we are wasting our computation power, let us see the different scenarios we could have. Let's say the mask vector we have is like this. So the green ones show the active or true lengths. So for this case, where all the lengths are active, we will execute all instructions for then block for every length of the vector, but we will also execute all instructions for then else block. But then, because the masks are false for all of them, we will discard all the results. So the gray color shows inactive lengths. If one is false and three is true, then for three of them we do the then block. Then for one of them we execute the else block. If two is true, two is false, it would look like this. For the three false, one true, it would be like this, and this is all false. So let's look at these pictures. No matter how the true and false element files lengths are distributed, we are always ending up wasting half of our computation power. So the number of green rectangles in each case is exactly the same. And this is true as long as the number of instructions inside the then and else block are the same, like the same. So the challenge we are facing is wasting the vector lengths. And to solve this problem, we are proposing our compiler path, which we call it active length consolidation, or ALC. So We first propose a simple algorithm for something we call permutation. Let's say we have these two vectors, and you see the corresponding mass vectors for them. The gray elements are inactive lanes, and the white ones are active or true lanes. What we want to do is to put all active lanes we could in the first vector and everything that remains in the second one. So if we do permutation for these vectors, we will end up something like this. So now you see the vector in the left side is completely true. We call it a uniform true vector. And the right one is a combination of true and false cases. And we are doing this with those vector manipulation instructions that we know that they are very fast. Okay, having this permutation, we propose ALC as this. So it works like this. In each iteration of the loop, we have two vectors that are the loop iterations. So the content of the vectors are the indices of the loop and the conditions they have. So we do the permutation for these two vectors. Then we see if we have a uniform true vector, we execute the then block only for those vectors, those indices. And if we don't have, it means that we have a uniform false vector. So for that one, we execute the else block. The thing is that we are always now executing one block, either then block or else block, and we are not linearizing the code. So we are fully utilizing our computation power. So then the other vector is passed to the next iteration, and then it goes on the same way. So this is a very high level view of how ALC should work. And now we want to see how does it actually perform. For the experiments, of course, we are using Fujitsu A6450X processor with 32 gigabytes of RAM. We know that on Fujitsu processor, the vector length is 512 bits, which is a long vector. And we are comparing against ARMClang compiler, the vectorization that is done by ARMClang. To test the performance, we provided a simple test kernel, which represents a good candidate for ALC. So the whole structure is like before. We have a for loop, we have an if then else statement, and inside that there is a lot of arithmetic operations, a lot of load instructions, and store operations. Okay, so we measured the speed up that we get for both ALC and ARMClang vectorization over the scalar code, and the scalar code is the result of compiling the code with Clang authority pipeline, but disabling the vectorization explicitly. When we do the measurements, we get something like this. So you see that ARMClang vectorization is making the code 2 times faster, while ALC is making it 8.88 times faster than scalar code, which is quite significant, but it still is slower than ARMClang vectorization. So this made us think, what is wrong with ALC? We were trying to find the bottlenecks, and the first thing that we guessed might be the problem was the permutation of it, because we are adding some more instructions to do the permutation. But we know that SV vector manipulation instructions are so fast, so this should probably not be the case. And when we did our measurements, it proved that only less than 5% of execution time was spent on the permutation. So to find the problem, we measured more metrics, and we got this, excuse me. And we got these results for memory stalls. So here you can see that ALC, these are the number of cycles that the pipeline is stalled due to memory operations. And you see that ALC is introducing 10 times more stalls due to memory. So next, we were trying to understand why this is happening. The problem lies in the uniform blocks that we are executing. So remember this part of the algorithm where when we have a uniform vector, we execute either the then block or else block for that uniform vector. So let's concentrate, for example, on the else block. We now take this simple example. We are going to execute this else block for this vector of uniform indices. So to do that, we need to load following indices of arrays B and C. We need to load E0, 5, 9, 13, and corresponding ones for C, and then store back to those indices of array A. But we are doing this in a single instruction, single vector instruction. So we are using gather load instructions that are proposed by SV extension. So if we want to look at what is happening in the memory, we are touching these non-consecutive memory addresses in a single instruction. And this is why we are just getting a very high latency. So in order to fix the problem, we need to eliminate gather instructions. We want to use the regular vector loads that load from consecutive memory addresses. And our solution was a modification that we call this data permutation. So remember that for ALC, the current implementation was we just permuted the vectors of indices of the loop. But in this version of ALC, we load all indices of all arrays that are used inside the denials block. And then we permute these arrays as well as the indices in each iteration. So doing so, we see that we get these results on memory stalls. Now we see that the memory stalls are reduced by almost 40%, and still it's much more stalls than compared to ARM-Clang, and this is because you're still using scatter store instructions, which are quite the same thing. They're storing in the non-consecutive memory addresses. But even with this 40% improvement in the memory stalls, we get a considerable improvement in terms of number of cycles. So here we see that the data permutation version of ALC not only works better than ALC, but it also now outperforms the ARM-Clang vectorization. And this is by knowing the fact that we are executing so many more instructions. So ALC, the previous version, and ARM-Clang are executing quite the same number of instructions, but the data permutation, because it's loading excessive data and is permuting every single vector of data, it's adding so many more instructions to the logic. But with that, we are still doing better than ARM-Clang vectorization. Okay, so yeah, as we saw, we are executing around 70% more instructions, but we are still getting around 9% more speed up. And there is a room for more improvements by eliminating scatter stores, which we are still working on. So if we want to have a single takeaway from this presentation for Ookami users, is that you should be warned that gather and scatter instructions are not good at all in Fujitsu processor. Thank you.
Thanks a lot. That was very interesting. What to think about. Any questions from somebody? Nothing. Maybe I can mention we also did like was at the very beginning of the Ookami project. We also did like a comparison of scatter operations with the different compilers, and we saw huge performance differences there. So that's probably nice to know there. The version which you compared to the ARM compiled version, which compiler did you use for compiling that one, the GCC or the GNU compiler?
We use the ARM-Clang compiler for the one we compared with, and we used our pass is we first compile with Clang, and then we run our pass. We use a specific SV intrinsics, so the code is then compiled with ARM Clang to get the binaries.
Okay, got it.